Very recently, we have learned the fundamental theorem of calculus. Basically tells us how to take a definite integral. Not too bad. Well, it turns out there is a second fundamental theorem of calculus too. And this second fundamental theorem is going to show us how integrals and derivatives are kind of connected. We already know they're inverses. If you take the derivative of an integral, you're back to the original function. If you take the integral of a derivative, you're back to the original function plus c. So it's all going to come down to, it's going to come down to this. We have two ways to look at a definite integral. Is it going to be just a number like the area, or could it still be a function of x? And here's what I mean. On the first example, I have a definite integral. I'm going from one number to another. I'm going to let a and b be a constant value, be a numerical value. And if you do that, you're going to come up with an answer that is pretty much some kind of constant. I don't know what it is. It's going to be the area underneath the graph to the x-axis. That's what it represents. But it is going to be a constant. If, however, you plug this one in, you're going to get big F, and I'm going to plug x in first, and then I'm going to plug a constant in. The second part will be technically minus f of a, which is a constant. And by the way, subtracting a constant, same as adding a constant. Any way you look at it, if you have two limits that are constants, your answer is going to be a constant. If you have one that's a constant and then one that's a variable, your definite integral will wind up as a function. You will actually see a function there with variables inside of it. That's an important distinction here. The second fundamental theorem of calculus is talking about the second example there. What happens when you take a definite integral and you get a function out of it? So here's how the second fundamental theorem goes. It starts off almost the same. If f is continuous on an interval. Oh, but this was a closed interval from a to b. This is an open interval, some kind of open area that just contains the point A. Now, here's where it changes. For every x in that interval, and I'm going to stop here because I have another question for you that's going to finish this problem up. What would happen if I decided to take the derivative of this function right here? I'm actually going to change this just a little bit. It turns out when you write this out in notation, a lot of times they'll use a different variable here. It doesn't matter what the variable is. They're just trying to emphasize the fact that, hey, I have a function here and I'm going to plug x into it. But I just forgot that's the way it's usually written in books. So what I'm going to ask you to do is take the derivative of each of these functions. Well, if we're taking the derivative of a definite integral, that's just bloody boring. Because we know that when you integrate this, you get a constant. What's the derivative of any constant? If you said 0, congratulations, you're correct. So basically, even though derivatives and integrals are inverses, if you're plugging in just plain old numbers, you'll always get the answer 0. And that is not what we're here for. No, my friends, the second fundamental theorem is all about what happens when you take the derivative of a definite integral that is a function of x. So I integrate this, I get capital F, the antiderivative of the top or upper limit minus the lower limit. We already said it doesn't matter if a is a constant, we know that is going to be a constant. When I take the derivative of these, the derivative of any constant is 0, but the derivative of an antiderivative is just f of x. This second fundamental theorem of calculus is actually just telling us the derivative of an integral is the original function, provided it's a function of x. This is the completed theorem. You take the derivative of an integral, you wind up with the original function. But it only works if you have a variable here at the upper limit and a constant at the lower limit. We'll do a bunch of examples in just a moment.